Okay, great. I have sent you an example in the chat. So if you can download it. So this is extra material for the initial condition and linearization constant calculations. I prepared this example just to show you, things can be done without memorizing all these equations of linearization constants and initial conditions and so on. You can start from the basics and you can go forward in calculation and you can get all the requirements. So no need to memorize any of such formula for calculation of VD, VQ, ID, IQ, EQ prime, EFD, V infinity and delta and K1 up to K6. So let us see this example. You can download it from the chat. The data of the system shown are M per unit, except M and the time constants are in seconds. Find the initial conditions. How many initial conditions? How many variables that we need to find the initial values? How many? If we enumerate it.
8.
8. You are right. VD, VQ, ID, IQ, V infinity and the delta, and then EQ prime and EFD. So we have 8 variables. You can get the initial values if you are given such data. The data here is the generator. The inertia of the generator is 10. Time constant, the field time constant is 6 seconds. Damping coefficient is 0. XD, XD prime, XQ, automatic voltage regulator. This is, I think this is 0.1. It should be 1 second is too much. This could be, let me put it in display format. Okay. So you have TA equal to 0.1 second, Ka equal to 100. Line here, resistance equal to 0, reactance equal to 0.4. Load equal to 0, there is no load here. BE, the initial condition, is characterized by the power, reactive power, and the terminal voltage. Real power, reactive power, and the terminal voltage is given here out of the generator. So, based on this operating condition or operating point, we need to find out all the initial conditions. So let us start from scratch. So you know that BE and the QE can be calculated as S output of the generator equal to VTI conjugate. VT equal to VD plus JVQ, ID conjugate minus JIQ. And then you can derive that VD equal to, or BE equal to VDID plus VQIQ. And it is given the initial value of the operating condition here, the power equal to 1. So this is one equation, VDID plus VQIQ equal to 1. And also QE, you can write it 0.4 equal to, from this equation, you can write VQID minus VDIQ. Here we need to, we can eliminate ID from these two equations by multiplying this equation by VQ, and we multiply this equation by VD. So this term will go together. So you can have, this is VQ times 1 equal to this, and VD times 0.4 equal to this. If you subtract, then you can write VQ minus 0.4 VD. This will go together. VQ IQ plus VD, VQ square plus IQ plus VD square IQ. So you can take IQ as a common factor here. So this is equal to terminal voltage, and the terminal voltage is given by 1 per unit, whatever. This is 1 per unit. Okay. So this is VT square plus times IQ, and the IQ you can relate it to VD, and you have an equation VD equal to XQ IQ, or IQ equal to VD over XQ, طبعا XQ equal to 0.5. You can write IQ equal to 2VD. So here, this is 2VD, and this is known. You can substitute it here, equal to 1. So in this case, you can find a relation between VQ and VD. So you can write VQ equal to 2.4 VD. Having the VT square equal to VQ square plus VD square, you can substitute on the VQ here equal to 2.4 VD plus VD square here, square plus VD square, equal to terminal voltage, which is 1 given in the equation, the operating condition. So you can write this, and you can end up with VD square. You can get the VD. Definitely, you can solve this equation to get the VD. Once you get the VD, you can go here and substitute for VQ. If you have VD and VQ, so if you have VD equal to XQ IQ, or IQ equal to 2VD, so you can get the IQ. And if you have VD, ID, VQ, IQ, so the remaining here is ID. VD is the known, VQ is known, IQ is known. So you can get the ID from the first equation. ID equal to VE minus over, then you can get the ID. So we have the ID, the VD, the ID, the IQ, the VD, the VQ are now calculated. So if you know the VD, the VQ equal to EQ prime minus XD prime ID, from this equation you can write or EQ prime equal to VQ plus 0.2, which is XD prime ID. طبعا this equation must be memorized, this algebraic equation, and also the model of the machine. The 4 differential equations, delta omega dot, delta dot, delta EQ prime dot, and delta EFD dot, and the algebraic equation, this should be known. This this is the basic equation that we are working with all, in designing the controller later on and so on. So for these equations must be memorized. So you can write here EQ prime equal to VQ plus 0.2 ID. All are known, so you can get EQ prime. And from the equation of EQ prime and EFD, you can write here, okay, you can jump to EFD, or you can get the V infinity and the angle. Okay, let us see the V infinity and the angle. From from this circuit, as we mentioned earlier, you can write the current here out of the generator equal to VT minus V infinity over the impedance plus VT times the local load. If the local load equal to 0, So we can easily write that I equal to Vt minus V infinity over J.4. So you can write I equal to ID plus JIQ. 1 over J.4 equal to minus J 2.5 multiplied by Vd plus JVQ minus V infinity D minus V infinity Q. So you can write this equation, ID equal to the real parts here and the IQ equal to the imaginary part of this. So you can end up with this equation. ID equal to 2.5 VQ minus 2.5 V infinity Q. Of course, the ID and the IQ are given or calculated, so you can get the V infinity Q. And also for IQ here, the imaginary part, you can write the IQ equal to this equation. The IQ and the VD are known, so you can get the V infinity D. Of course, the square root of V infinity Q square, V infinity D square gives you V infinity, and you can get tan delta equal to V infinity D over V infinity Q. Look at tan delta here. Tan delta equal to tan inverse V infinity D over V infinity Q. And this is why, and usually when you get the angle, we say the imaginary part over the real part. But here, we define delta as the angle with the quadrature part. So this is V infinity, and this is delta. So we define delta here at the angle with the quadrature, not with the direct axis. So this is why we have it here V infinity D over V infinity Q. So you can get the delta, the initial angle, and definitely from the EQ prime equation, if you put here EQ prime dot, you have this equation EQ prime dot equal to 1 over TDO prime multiplied by EFD minus EQ prime minus XD minus XD prime ID. So for the initial value, this is equal to 0. So this is equal to EFD equal to EQ prime plus XD minus XD prime times ID. These are parameters given. ID is known, EQ prime, so we can get the EFD. So the EFD also is known. There is another two parameters or two variables or two references quantities that we need to get. We need to find also BM 0. We need to find also V reference 0. So we need to find now an additional two values. احنا we get now 8 values اللي احنا قلنا عليهم في الاول VD VQ ID IQ EQ prime EFD and V infinity and delta. So these are the 8 variables that we need to get. Also, in addition to these, we need to find how much BM0, how much V reference 0. So what do you think to get those values? Any idea? Any idea, Shabab? How much will BM0? The initial value of the mechanical power, Hussein? Hussein?
Initially, it's equal BE.
Yes, it is equal to BE. BE 0, which is 1 per unit. Simply at the steady state, will be mechanical equal to B electrical. This is the initial value. This is the reference value for the B mechanical. So equal to B electrical equal to 1 per unit. How much will be reference now? Any idea? If you have any idea, please raise your hand. How much will be reference 0? How much of the reference voltage that gives you terminal voltage equal to 1 per unit? Now we need to fix the terminal voltage at 1 per unit. How much V reference then? In order to have terminal voltage equal to 1. So what do you think? Ramadan.
EFD K.
We couldn't hear you, Ramadan. You have a problem with that.
Can you hear me now?
Yes, now it's okay.
We can calculate the reference, which is equal to EFD divided by KA plus VT.
Okay, great. So you want to say from EFD dot equation, this is 1 over TA multiplied by KA times V reference minus VT minus UBSS minus EFD, right? From this equation, yes, this is equal to 0 at steady state. UBSS also equal to 0. There is no oscillation. There is no impact of the power system stabilizer. So you can write here, and this is equal to 0. So you have KA times V reference minus VT minus EFD equal to 0. So EFD, you can write here EFD equal to, or V reference equal to, so this is could be go equal to this. So KA plus PT. So you can write here V reference equal to EFD, which is already calculated, over KA plus VT. So you can get the reference voltage here. Okay. So in addition to these 8 variables, we can have a V reference, and we can have mechanical power. I don't know what is given here or not, but you have to. You can say V mechanical equal to. You can add it here. V mechanical equal to 1 per unit. Okay. So what I want to emphasize here, without having this matrix equations of FYD and YQ and FD and FQ and all these, this is could be helpful in coding the problem, in solving the problem or coding the problem using MATLAB or so. So these equations will be very helpful. I think you have a closed form for VD and VQ and so on. But you can also go through the problem starting from scratch without knowing all these expressions. This is what I am emphasizing on. Also, constants K1 up to K6 can be calculated as follows. Let us continue this example. We don't need to memorize all these constants expression and so on. No, we don't need this. If I ask you by hand calculation, you can easily do it by hand calculation without knowing all these expressions. So we finished the initial condition. Let us see the linearization constants. Okay. Linearization constants, you have to know in the K1 and the K2 comes from the linearization of electrical power. ال K5 أو ال K3 ال K4 comes from ال EQ prime equation. EQ prime dot equation. ال K5 and the K6 comes from the terminal voltage linearization. Okay? And the key issue here is to find delta ID and delta IQ in terms of EQ prime, delta and EQ prime. And we need to relate ID with delta and EQ prime and IQ with delta and EQ prime. Once you get this, you can get the VD or delta VD, you can get the delta VQ, and then you can start linearize all these parameters. So this is VQ, which is EQ prime minus 0.2 ID. This is, of course, this is the algebraic equation. This is XD prime here. And the VD equal to XQ IQ, 0.5. So you can, this is the expression we already derived it in initial values, ID equal to 2.5. This comes from here. We already derived this equation, ID equal to this and IQ equal to this. What we want to do here, we need to replace the V infinity Q. How much is V infinity Q in terms of delta and V infinity? This is equal to what? Equal to V infinity sine or cosine. Sine or cosine delta. Ayub, Khalifa.
Cosine.
Cosine delta. As we define the delta, this is V infinity, and this is delta, and this is the quadrature x. So delta is defined with respect to the quadrature x. So V infinity Q, and this is V infinity D. So V infinity Q is V infinity, which is constant in V infinity. You already find the V infinity, and V infinity will be kept constant. It will not change. Whatever the system loading or system condition, this is the infinite bus voltage, and the infinite bus voltage is constant. So this is V infinity cosine delta, and this is V infinity sine delta. Of course, if V infinity is calculated, you can multiply by 2.5 here to get the coefficient of cosine, and also V infinity times this to get the coefficient of sine. So ID and IQ can be expressed as such. And you can replace the VQ in terms of ID, and VD also in terms of IQ. So you can have, this is VD and VQ in terms of ID and IQ. This is algebraic equation, VQ in terms of ID and VD also in terms of IQ. So you can go to this equation, ID equal to this, and you replace this by V infinity, definitely. VQ equal to EQ prime minus point this. And this will be multiplied by 2.5. So 2.5 multiplied by this value, minus 2.5 times V infinity cosine delta. So this is 2.5 times V infinity and the cosine delta. So this is ID. Similarly, you can write, okay, let us combine here. This is minus 0.5 ID, so you can bring it here 1.5. Normally you can manipulate. So ID equal to this. Now you can, okay, let us see IQ, and then we can linearize later. So IQ equal to, it's given from there, minus 0.25 VD, will VD equal to 0.5 IQ, so we can replace VD by IQ, and this is V infinity multiplied by sine. So we get here IQ, and of course you can get IQ in this 2.25, and then you can divide, so you can get the IQ equal to this. These are very important equations that we these equations will play the main role in linearization. In this case, you can get a delta ID in terms of delta EQ and delta delta. And the delta IQ, you can get it in terms of delta delta. This is not always the case. In the IQ, we don't have here EQ prime. This is not always the case. Probably due to this there is no load, local load or so. But generally, you can express IQ in terms of EQ prime and delta. So if you want to linearize this, so delta ID will be equal to this delta EQ prime cosine delta. How to linearize cosine delta? If you want to linearize cosine delta, so you get the derivative times delta delta. So this is the linearization of cosine. Type of sine, how to linearize the sine? Derivative, which is cosine delta times delta delta. So this is the this value. So we linearize this equation, linearizing the ID, delta ID equal to this, multiplied by this value, sine delta, where is it here, minus 1.5505. For cosine will be minus sine. So we have here, this is positive, sine delta, delta delta. And you need to replace, طبعا we are doing linearization around the initial operating condition. So this value is known, you know delta. So you can get sine delta and you can multiply and you can end up with this equation. So this is delta ID in terms of the states, delta EQ prime and delta delta. And also you can do this for delta IQ equal to, this would be cosine delta delta delta, and cosine delta you will replace it by cosine the initial angle, which is calculated there. So this will be multiplied by this, so you can have this delta ID and delta IQ. If you have delta ID and the delta IQ, then you can get delta VD and delta VQ. Delta VQ equal to delta EQ prime minus 0.2 times delta ID, and this is delta ID. So you have here a term with delta EQ prime will be combined with this one, and delta VD equal to 0.5 delta IQ. So you multiply this by 0.5. And you can get the deviation of all voltages and the currents. And this is the key points of electrical power, for example. So this is delta VQ and this is delta VD. From the delta BE, as we mentioned earlier, it's VD, ID, VQ, IQ. If you linearize these terms, will be VD, delta ID, delta VD, and so on. And VD, you can replace it by the initial value. And you can write here, this is VD0, and this is ID0, initial values. So you can have this. And of course, you can replace delta ID in terms of delta EQ prime and delta delta, and delta VD and delta IQ and delta. So you end up with one equation, or all these, terms, 4 terms here. You just substitute with these initial values, and you end up with this delta BE equal to, if you combine all these delta and delta EQ prime, so you have them as such. So this is K1 and K2. So delta BE, so this is K1 and this is K2. So are you following, Shabab? From this equation, delta EQ prime or EQ prime dot, of course you have here delta ID, and you can write here, if you want to linearize, so you can have, this is delta ID, and you can replace it by the equation that we derived earlier. Of course, you can replace this as such. So when you have this delta EFD, and you have this one here, and then you can you have this as such. So if you this is actually this is S, you have STDO prime 1 plus, then you have here delta EQ prime appears here again. So we'll take delta EQ prime on the other side, so it becomes 2 equal to this. And then you can, in order to have it in the standard form, you take 2 as a common factor. So if you compare it, you take 2 as a common factor. So this would be 0.5, and this would be also 0.5 multiplied by this. If you compare it with the standard form, which is 1 plus STDO prime K3 equal to this, you can, of course, you can write K3 equal to 0.5 and the K4 equal to this value. For terminal voltage linearization, K5 and the K6, this is easy also to linearize. If you want to linearize, you get the derivative here. So it becomes 2VT delta VT plus 2VD delta VD, and so on. So of course you have the terminal voltage is known, VD0 is known, VQ0 is known. You just replace it, and you can write delta VD equal to this. And you can express delta VD in terms of EQ prime and delta VQ in terms of EQ prime and the delta. So you have this equation, and you can combine, and this is equal to K5 and the K6. So this is K5 and this is K6. What I want to emphasize on, you can, by starting from scratch without having all these matrix expressions and so on, you can easily solve the problem. Is there any difficulty for hand calculation? Is there any difficulty or something? It is difficult to memorize here. But don't tell me about the model. Delta omega dot, delta dot, delta EQ prime dot, and delta EFD dot. This equation should be, of course, in addition to VD equal to XQIQ, VQ equal to EQ prime minus XD prime ID. So these are algebraic equations that must be known. Is there any difficulty? Is there any question? Ahmed, Suleiman?
Yes, doctor. So the model, the equations for the model, we should memorize. We should memorize all of them, huh?
Of course, this is the swing equation. It is not a big issue to memorize. Minus BD or D times delta omega. Delta dot equal to omega base times omega minus 1, delta. The EQ prime 1 over TDO prime times EFD minus EQ prime minus XD minus XD prime ID. And this is equal to 1 over TA, not over times KA, V reference minus VT minus UBSS or U or plus USS minus EFD. So this is the this is the model, and these are some algebraic equations. But no need to to write BE equal to VD ID plus VQ IQ. Then you can derive it if you don't know it. You just write VI conjugate, and you can get the BE, and also you can get the Q also. VE and QE. You can express it in VQID minus VDIQ. So, is it clear, Ahmed?
Yes, doctor. What about the standard forms for like K1, K2 up to K6? So this one also we should memorize it.
No. And we derived it here. And this is K5 and K6. Do we need to memorize all this formula of K5 and K6? No. You can, but you have to know the K5 and the K6 comes from the linearization of the terminal voltage. So this is the terminal voltage in terms of VD and VQ. If you linearize this equation, you can write 2VT delta, 2VD delta VD, 2VQ delta VQ. This is clear?
Yes, doctor.
VT
I mean the last part.
VD0 is calculated, VQ0 is calculated, so you can easily write this equation. The delta VD, we derived it in the delta VD in terms of delta from this equation. You have it here. This is VD and delta VD equal to this, and delta VQ equal to this multiplied by this. So we linearize the delta ID and delta IQ, and we get the delta VD and delta VQ also. This is delta VD in terms of delta delta. There is no delta EQ prime here. Delta VQ in terms of delta EQ prime and delta delta. So you just substitute on a delta VD with delta VQ in terms of delta delta and delta EQ prime in that equation. We just substituted delta VD and delta VQ here. And then you end up with this. This is simply K5 and this is simply K6. Okay, Ahmed?
Yeah, yes, clear, doctor.
You have to know also that K1 and the K2 comes from the BE equation. This is BE equation, linearization of the BE equal to VDID plus VQIQ. We have here 4 variables. So if you take the derivative or delta B E equal to, you can have it here VD delta ID plus ID delta VD. VQ delta IQ, IQ delta VQ. So, and you can have this equation, or these values are known from the initial conditions, and the delta ID you just express it in terms of delta delta and delta EQ prime as we have it before, and also delta VD, delta VQ, delta IQ, and then you end up with delta delta and the delta EQ prime. So this becomes K1 and this becomes K2. So we don't need to memorize all these. And we formulate it as such in order to develop a code for simulation of this. But with hand calculation also, for such a simple system, you can easily do it. Ramadan Ali, you have a question, Ramadan?
Yes, sir.
Yes, please.
This is omega B.
Sorry? Omega B is 377. Omega B is 377 radian per second for 60 hertz systems.
So our
this is the base. This is the base speed. This is the base speed. Okay. Your voice is not clear, Ramadan. Still not clear.
Okay, I'll change it.
You have your omega B here is 377. This is 377 times omega minus 1. Omega here is embryonic. This example number 2, طبعا of course we already يعني just Ramadan back. Okay. Good question, Ramadan.
Can you hear me?
Wallahi, unfortunately, no, not yet.
What about now? Can you hear me?
Wallahi, now it's okay.
Okay. In period, so omega will be 1.
Delta dot equal to omega b times omega minus 1, right? This omega embryonic speed, and this is the base value. This equal to 377 radian per second. This is embryonic, yani around 1. So this is the this one is the omega synchronous in baryonic. So this is the baryonic quantity. This is the baryonic quantity, omega minus 1, or we can write it as delta omega. The omega deviation between the the speed and the synchronous speed. So this is delta omega, omega minus 1, and this is omega base, which is 377.
Okay.
Is it clear, ya Ramadan?
It's clear.
Okay. So this, of course, you can go straightforward and do this, and this is already done. And I would like you to go through it by hand calculation in order to get experience and practice this. Do you have any question? Okay, so let us move to the probably this one. Okay, so let us move to the next, where we will address the question is how to improve the damping. How to improve the system damping to the low frequency oscillation. Now we are discussing the low frequency oscillation problem, and we need to increase the system damping in order to improve the system response. So let me put it in display form. Okay. So how to improve the system damping? In order to design a controller or compensator to improve the system damping, we need to, as we started before, we need to linearize the model. We have the linearization constants now. We can calculate it. So we can linearize the nonlinear model, which is delta, not delta, omega dot, delta dot, EQ prime dot, EFD dot. This is the nonlinear equations. We can linearize it to delta E, delta omega dot, delta delta dot, and so on, having these linearization constants. So we need to write, at the end, we need to write the system as x dot equal to x plus bu. So we can check the stability based on the eigenvalues of A, and we can design a controller based on the linearized model, and we can see the closed loop matrix if we have a controller, and then we can see the eigenvalues of this AC matrix, and we can evaluate the effectiveness of the designed controller. If we have the eigenvalues shifted to the left more and more, that means the system becomes more stable, and the stabilizer or the compensator design is working fine. So we need to see how to improve the damping of this system. So we will see the damping requirement, the stabilizer versus stabilizer, the input signals of the stabilizer, the structure, also different structure of the stabilizer, and state equation x dot equal to x plus pu. And we can also calculate the damping and synchronizing torque. We know about the synchronizing torque before, or synchronizing power coefficient, or synchronizing the torque coefficient. We did it earlier in linearization of the steady state stability. We need to, based on the block diagram that we showed you before, we need also to derive the damping and synchronizing torque coefficients. So as we discussed, then this is the frequency range, and we also already covered these parts, and we need to design a controller in the excitation system, and this controller has the name of power system stabilizer. This power system stabilizer will inject, this is VT, and this is V reference, positive, negative, and you have here the stabilizer, power system stabilizer controller. This is UPSS. This is the control signal, which could becomes here positive. So that was the supplementary feedback stabilizing signals in the excitation system, in this summing point. B power system stabilizers augment the power system stability limit and extend the power transfer capability by enhancing the system damping of low frequency oscillations. As we mentioned, this low frequency oscillation problem comes with the interconnection of the systems. When we have two utilities are connected with weak tie, weak line, or weak connection. Weak tie means what? Reactance is high. Long transmission line, reactance is high, and power transfer is limited. V1, V2, V sine delta. So this is high. So we have here. So if we can provide a controller that can extend the power transfer or improve the power transfer, if it can push the stability limit, relax it or extend it, that would be great. The utilizing of supplementary excitation control signals for improving dynamic stability power system has received much attention. This has started, as we mentioned earlier, from 1969 with this DeMello and this Phillips Heffron model. Of course, this starting from 1969, and the people, started developing this linearized model and so on. So nowadays, the conventional power system stabilizer, which is still used nowadays, the structure that is widely used in all the utilities worldwide is a lead lag structure, K1 plus ST1 over 1 plus ST2. Simply, you can repeat this stage, so you can have here two stages or three stages, or you can use different time constant, 1 plus ST4. So you can have 2 or 3 states with different time constants. If the time constants are equal, so you have here this equal to multiplied by 3 or so on. So it's widely used for power system utilities. In recent years, several approaches based on modern control theory have been applied to PSS design, but so far, all these modern control theory optimal control theory, intelligent, nonlinear control, all these are still in research area. Personally, I don't know any utility worldwide that implement such sophisticated techniques. I know the stability of the system, they are very happy. The utility engineers are very happy with this simple structure, robust structure. And although if you go for modern control or optimal control, you can reshape the eigenvalues. You can put it anywhere as you want, and left-hand side. Yeah, you can do a lot of fancy things, but in real life, the utilities still have such structure. These include optimal control, adaptive control, variable structure, intelligent control. These are the modern, control theories. Okay, now let us see what is the purpose of that damping controller. What do we need from this controller actually? We can look at the swing equation and see. And you have here the swing equation is omega dot equal to 1 over m B mechanical minus B electrical minus if you have damping power اللي هي BD اللي هي D times delta omega, D times omega minus 1 or delta omega. This is okay, that's fine. Assume that this is 0, let us take it out. Now, if we have any disturbance like a fault, what will happen for this equation? Which term will be disturbed, BM or BE? Which term will be disturbed more? Ahmad?
BE, doctor?
طبعا الBE electrical power will change لأنه طبعا of course assuming حتى even the the worst case scenario, this is the generator and this is the infinite bus. Assuming that we have here 3-phase fault, solid fault. How much is the voltage here? How much is the terminal voltage during the fault? Hussein?
0.
0. How much is the electrical power output of the machine?
0.
0. So this is the electrical power output. BE will be disturbed. And when we have this fault here, definitely BE, even if it is not 0, this is an extreme case. If it is not 0, it will be reduced, right? Even if you have a fault here, you have double line and you have fault at the midpoint. So you have some power transfer, but this power transfer will be definitely lower than the steady state value. Am I right? So eventually we can say BE will be reduced, right? So in order to minimize the difference now, in order to minimize the difference between BM and BE, if you can add a controller that gives you an additional term here, which is you can say this damping مثلا or K times you have here this BE. You need here a term that will be equal to K times delta omega. So you can add here a term which will be here minus also, يعني this will be K times delta omega will be added to BE. يعني you can have this equal to omega dot now equal to 1 over m BM minus BE plus some kind of damping here would be input here of delta omega. Okay, so this will be added to the damping power here if you have V times delta omega. So you can increase the damping here by adding a term with K, or the damping coefficient here, and this term should be in phase with delta omega. Yani the damping term that is needed from the stabilizer should be in phase with delta omega, should increase the total damping that we have here. And this is the idea. This is the idea of or behind the power system stabilizer design. We need a controller to give us a damping power which in phase with delta omega. So you can, of course, have this torque phasors in delta omega. Hussein Ali? Hussein, you have a question?
Yes, doctor.
Yes, please.
Doctor, in the original equation, we have this damping coefficient multiplied by the delta omega, which is doing the damping work here. Why we do need to introduce something which is related to the B electrical to do similar, let's say, similar role or similar action to the damping term here?
This damping term, this damping is like you can look at it as friction, windage of the machine. So this term is damping here is constant, doesn't change. Did you get the point?
Yes.
Now we need, during the dynamics, during the oscillation, we need a term here in order to improve the damping. And this damping term, yes, it will appear, but this D is constant. It is embedded in the, or a property of the machine. What we need is to enhance the damping by adding an extra term, comes from the controller. And this one will not be able to damp the oscillations. Now we need a supplementary controller here. Did you get the point?
Yes, doctor.
So this damping comes from the friction, windage, and so on. But this is not enough to damp the low frequency oscillation. So we need a controller through the field excitation system in order to increase the damping, in order to be added to this term, in order to enhance this damping term. So we have another here constant, like say K مثلا, and this K will be also multiplied by delta omega. So they are in phase with delta omega. This term will be also in phase with delta omega. So when you have this delta and delta omega axis here, so this is the electrical torque, and the opposite is mechanical torque. So of course they are Tm minus Te, and this Te has two components here. You can have one component which is, comes to delta, and we can write this as a synchronizing coefficient, and this is the damping coefficient, Kd times delta omega. So what we need from the extra controller or the power system stabilizer is to give us a force or a component here in this term is in phase with delta omega. So you can write delta TE here as such. Considering a small oscillation, the swing equation can be linearized, resulting this. And to derive an extra damping torque, delta TE, through the excitation must be in phase with delta omega, as we mentioned. طيب, let me ask you if we need to develop a controller in mechanical part through the governor. Okay, so this torque comes from here, from the controller and the governor. What is the relation between this delta T that comes from here with delta omega? What do you think? Would it be in phase with delta omega or out of phase with delta omega? Would it be in phase with delta omega or out of phase of delta omega? If you need to reduce the difference between BM and BE. Hussein? Hussein?
Yes, Doctor. In phase.
In phase or out phase?
No, in phase. In phase with delta omega.
حتى even it comes from BM. أنا عايز تقول إنها تبقى BM plus a constant multiplied by delta omega minus BE. يعني أنت عندك during the disturbance. طيب نشوف. Okay. During the disturbance, the BE will get lower. Am I right?
Yes.
And you add here a positive term. So that means you are degrading the system stability.
Accelerating will be mechanical.
What do you mean?
Yes, it should be out of phase, because if it is in phase, the B mechanical will increase, so we will accelerate the shaft.
This is exactly the case. So we need, if we are designing a controller in the governor system, not in the excitation system. In the governor system, we need this controller to give us a component here out of phase. This should be minus in order to minimize the acceleration power. And then if we have a controller in field or in excitation system, we need this controller to give us a component in phase with delta omega. Am I clear on this? So if you have here a controller that will enhance the electrical power, it should be negative, minus K times delta omega. So you have it here in phase with delta omega. And طبعا the minus D will, of course, will take here. It will take this as a common factor. So this will be plus K times delta omega. So it becomes, and here, if you add a controller here, you need this controller to be out of phase of delta omega in order to minimize, and this will be getting lower, and you have acceleration, so you need a damping controller to reduce the acceleration here. Saad Ahmed?
Yes, Doctor. I wanted to ask, since the duration of the fault is usually very less, why would we want a controller in the mechanical part of the system?
I just said no, if.
Oh, okay.
Okay, so maybe if you expand the time, in dynamic stability, maybe we need مثلا for up to 5 seconds. We need to study the system up to 5 seconds. Then in transient stability, we need it probably 0.1 second or so. Maybe if you expand this, yani if you expand this time, I need to simulate the system to 40 seconds. In 40 seconds, you can take the effect of the governor and the mechanical system. And if you need to design a controller in mechanical system, this should be the case. Okay? You have to develop a damping controller out of phase of delta omega. Is it clear?
Yes, Doctor. Thank you.
Okay. So this is for the electrical torque, and this is for the mechanical torque. Where the governor must be in phase with minus delta omega or out of phase of delta omega. So you can write delta Tm equal to any change in mechanical power will be minus delta. Electrical power will be in phase with delta omega. And when you linearize the swing equation, you can, of course, write omega dot to be ms times delta omega here. If you have mechanical damping comes from the mechanical system, damping comes from the electrical system, and this is the initial D damping coefficient here times delta omega equal to K1 plus delta delta. If you take the delta omega equal to this from delta dot equation, or delta dot equation equal to omega b delta omega. So you can write here S delta over omega b equal to delta omega. So you can substitute here, and you can take the you can write it as a standard form of the second order system, and then you can get the zeta n and omega n. And of course, you know omega n already. We derived it earlier. Omega n is defined as square root of 377 times K1 over the m, the inertia of the. This is the natural, or this is the undamped natural frequency, or natural mechanical mode oscillating frequency in radian per second. Of course, if you want divide it by 2 pi, then you can get zeta n. You can write zeta n based on that equation. If you compare, you can write zeta n here equal to this over omega b times 2 times omega n natural frequency that you have here. Zeta n equal to dm. You have damping from the mechanical power or mechanical system, and dE plus dE. So if you increase the damping, whether from the mechanical system, whether from the electrical system, you can of course increase the zeta. If you increase the zeta, the oscillation will be lower, of course, or the damping will be higher. So okay, it's clear that the supplementary will increase with either you have a controller in the governor system or a controller from the electrical system, whatever. And as I mentioned, an electrical system, you need it to be in phase with delta omega. For mechanical system, if we need to have it out of phase of delta omega. So we will concentrate, of course, on the excitation system. So we need our controller to provide us a component in phase with delta omega. Okay, so this is our target here behind the controller design. So this is the block diagram. We already showed this block diagram in linearization process K1, K2. These two components together represent delta BE. These two together. So we have here delta Tm minus delta Tm minus delta Te and you go to, you have here delta omega, you have here delta delta. These are the states, delta EQ prime and delta EFD. You have 4 integrators here. And the terminal voltage, these two components together are the terminal voltage. This plus this is the terminal voltage. Delta VT equal to K5 delta delta plus K6 delta EQ prime. So you have here K5 comes from delta delta and the K6 comes from delta EQ prime. So this is delta VT. If you want, you can add here also delta V reference. If V reference is changing, مثلا, for example, 10%, if you do some disturbance here. Otherwise, of course, delta TM will be 0. There is no change in mechanical power. There is no change in reference voltage. So this is K3 that we derived the K4 here, and the K1 and the K2, K5. So this is the block diagram of the linearized model. This is the first equation. As we see, this is the second equation, this is the third equation, and this is the fourth equation of EFD. So let us see the idea of supplementary. Hussein, do you have a question, Hussein?
Yes, doctor. We already just said that the integrators we are going to use the K by 1 plus ST1 over 1 plus ST2.
Okay.
Is it? But we are not using them here.
Again, Hussein, please.
We just said that we are going to use the standard integrators, which is the K constant multiplied by 1 plus ST1 over 1 plus ST2, isn't?
This is the stabilizer.
Yes.
This is the stabilizer transfer function. This is the power system stabilizer. This model is the linearized model for the machine. Linearized model for the machine only, without stabilizer.
Okay.
Is it clear?
Yes. Clear.
What we will do later, we will integrate the stabilizer to this. If you assume, for example, this is your stabilizer. This is the BSS transfer function here, and you get, for example, delta omega, and you have UBSS, output. This is the output of the stabilizer, and you take a signal from delta omega here. Okay? So you can integrate this to this block diagram. This is delta omega. So let us take this signal here with the stabilizer BSS, and the output of the stabilizer will be UBSS. Here. So this is the stabilizer now. Is it clear, Hussein?
Yes, it's clear now.
So the basic, this basic block diagram for the machine. And if you have a stabilizer, but this is what be the stabilizer here. So the idea of supplementary excitation control, known as the power system stabilizer, to apply signal through the excitation system. This is summing point of V reference and the terminal voltage, but it will go through the excitation system. This is the block that represents the automatic voltage regulator. So the signal that comes from the stabilizer will go through the excitation system here to increase the damping torque of the generator. As shown in the block diagram of the linearized model, the power system stabilizer output UBSS is applied through the TA, TDO prime, and the K2 blocks. It will go, this signal will go through this block and will go also through this block, and it will go through this block. Am I right? And if we have a stabilizer here, the output of the stabilizer will go through this block and will go through this block and also will go through this block. Am I right? Is it clear?
Yes, sir.
طيب, let me ask you, this block gives us leading angle or lagging angle. يعني when you have a signal here with angle مثلا, for example, 30, what do you think the angle would be here? Greater than 30 or lower than 30? In other words, this block will give you, or the angle of this block at any oscillation frequency is equal to j omega. Okay, so what is the angle of this block, positive or negative?
Negative, doctor.
Negative, yes, of course. The angle here is 0. The angle of the numerator is, of course, the imaginary over the real. So the total angle is numerator minus the denominator. Am I right? And when you have Ka over 1 plus STA, 1 plus j omega Ta. So what is the angle of this? This angle is the angle of Ka minus the angle of the denominator, which is 1 plus j omega Ta. This angle is tan inverse omega Ta, tan inverse. This is the angle. This angle is 0. So 0 minus this angle. So the final angle of this block is negative. So this would be less than 30. And you have here a negative angle. So if you multiply this signal with angle 30 with a negative angle here, so you add these angles together, so definitely this will be less than 30. Am I right? And this block gives you, طبعا time is over, فانتوا definitely you let us continue next class إن شاء الله. لأن this is very important point. And based on this point, we will go to design this power system stabilizer. And this is why this is very important point. لأنه based on this point, we will see the conditions under which we can provide a signal from the stabilizer that will be in phase with delta omega. That's as we discussed earlier. And we need a component of the damping power that is in phase with delta omega. So we will continue next class, inshallah. If you have any question, please you can ask. Otherwise, you can leave. And as you know, later we will start, inshallah, at 9 o'clock or 9 p.m. starting from Wednesday, inshallah.
Doctor, for the reading assignment presentation, how much should we plan for the time, for the presentation time?
It will be on Wednesday, as we mentioned, right?
Yes, but how much should we plan per presentation?
You have to plan for not exceeding 10 minutes.
10 minutes.
10 minutes is maximum.
Okay, noted.
Okay, and if you finish in 8 minutes, 7 minutes, that would be great also.
Okay, but so I think some of the material is big. Maybe it can't fit in that time.
Well, actually, no, time is very limited. We are very tight now. With this, having the exams shifted earlier, and also the Ramadan time, you can see the constraints that we have. So we have to squeeze things also. It's very difficult to spend 2 classes in the presentations. Now we still have some material to be delivered, right? It's
Okay.
very difficult to have 2 classes for presentation. We will dedicate only one